Uh, Today we start on chapter 3, which deals with electrons in a periodic potential. And electrons in a periodic potential tells us or describes to us what happens in a single crystalline solid. So that automatically takes us to the concept of energy bands in solids. So let's start by talking about different types, different structures of solids, and how we distinguish between these different structures. And the very first and important structure of a solid is the single crystal form of a solid. So in a single crystal solid, we have a long range order present in the location of the cores or the atoms in the solid. And before we talk about this long range order, let us work with a very simple mathematical model or a mathematical abstraction that we could use in describing single crystalline solids. And the mathematical abstraction that we want to work with is when we have a geometrical array as the one that we see here in this figure. Here in this figure, we have different points arrayed systematically in space with certain periodicity and certain order. So we see several parallelograms, if you like, placed adjacent to one another. So this mathematical structure is called a lattice. Lattice is a periodic arrangement of points in space. And here, if we take this parallelogram and this lattice, this mathematical lattice is in 2 dimensions, because that is what I'm able to show you here in this 2-dimensional screen or 2-dimensional paper. So if we take this 2-dimensional unit structure, which has the 4 corners of lattice points, and this is smallest unit that we have is called unit cell. And what we can see that is we can translationally move this unit cell with a certain translational order, and we can create the whole lattice space or the whole 2-dimensional lattice. So the 2-dimensional lattice can be created from this unit cell by translationally moving or translationally moving this unit cell in a particular order. So if we want to form a solid of any sort, which is a single crystal solid, what we have to do is fill up all these lattice points. Each point here is called the lattice point, with a single atom, or maybe a group of atoms, maybe 2 atoms, maybe 10 atoms, maybe 100 atoms, maybe thousands of atoms. Each point is filled with this number of atoms, which we call core, the core or the basis of the solid. So a solid is literally placing atoms or molecules or a number of atoms in each lattice point. So you can see that there is periodicity right, throughout. And this unit cell can produce the whole lattice by repeatedly translationally moving this unit cell. We can also locate each point, each lattice point, by simply choosing an origin and then drawing 3 axes to define a 3-dimensional space. Now again, here I have a 2-dimensional space, so I'm defining a unit vector or a unit dimension in one direction, which I'm calling A, and then another unit direction, which I'm calling B. Okay, this is in 2-dimensional case. Okay, so these are called the basis vectors. And these basis vectors are simply like the unit vectors when we have, a vector space, when we define a space and then we try to locate each point by a vector from the origin to that point. So these unit vectors, A and B, define this space, this 2-dimensional space. So for any lattice point, like this point, it can be written as 3A, so 3 along the lattice vector or the lattice basis vector A, plus 3B, right? Why am I saying that? Because you can see 1, 2, 3. So the location of this point is 3 units along the A axis, and then 1, 2, 3, 3 units along the B axis. So this point is 3A plus 3B. Similarly, this point here is 1A plus 2B, and so on. So we can define each point. And each point can be written actually as a vector R. Okay, so the vector R is written in terms of these, if you like, unit-based vectors. And we can define each point this way. Now, to form a solid, we have to place a core. A core is one atom or a group of atoms in each lattice point. So for copper, for instance, we place one atom of copper regularly in these lattice points, and then we produce copper. If we have a more complex solid, like for instance, a solid that has two atoms, then we place the 2 atoms, like say gallium phosphide, single crystal. So we have gallium and phosphorus. This would be the core. In some polymers, you could have hundreds of atoms for one core, because we know in a polymer, a molecule can be made up of so many carbon and hydrogen atoms and oxygen atoms, etc. So we can have so many atoms forming this core. Now, what distinguishes one solid from another solid? And we're talking about single crystal solids. That is, we have a lattice and we have periodicity and we have cores in each lattice point. What distinguishes one solid from another solid is the fact that the core atoms are different. Copper, aluminum, or gallium arsenide, or gallium phosphide, or even a polymeric molecule. That's one thing. The other thing is this unit cell. You can see here it's a parallelogram, and it's probably has an acute angle here of 60 and maybe an obtuse angle here of 120. So that's a special parallelogram. You may have another parallelogram where this is 90 and this is 90 degrees. So that would define a different geometry. Okay? And so on. So you can have different types of parallelograms defining different crystal structures. So that's what distinguishes a single crystal from another single crystal. And we also talked about the basis vectors, A, B, and C. Now, you don't see the basis vector C in this figure up here because we only have a 2D crystal. But if we expand this to three-dimensional space, then we will have a third basis vector, which is the C vector. And as I've just shown you in the previous slide, the position R, like this one here, of any lattice point can be written in terms of integers n1 and n3, which define the location of the point with respect to an origin here. Okay, so if we need to make a solid, then we simply need to create the lattice, that's the mathematical abstraction, and then look at the unit cell, how it is shaped or formed, and then use the unit cell to produce, the lattice points, all the lattice points by translationally moving the unit cell. And then we can define each point. Okay? Then, if we want to create the single crystal solid, we have to add the building blocks or the cores, which could be one atom in simple crystals like copper or silver, but it may contain many thousands of atoms, as in complex organic protein crystals. And you could have organic protein single crystals. So you need a lattice structure to describe that. Okay? So the basic fact is that the lattice in a space is created by this unit cell. So you translationally produce the lattice by moving this unit cell. So in other words, if we move this unit cell here, we have this point, and then if we move it translationally here, we get these points, and we move it translationally here and translationally here, and we create all the lattice space. So the unit cell is a very good representation of the single crystal structure. So that immediately takes us to, focus more in the unit cell, because it distinguishes one single crystal solid from another single crystal solid. Okay? One of the most important structures for single crystal solids is the simple cubic structure, SC. And now we're going to be talking about a three-dimensional solid, because in reality, solids are three-dimensional. So the unit cell is a cube. So think of the parallelogram in a two-dimensional solid, and think of that parallelogram becoming a square, equal sides, and an angle that is 90 degrees. Now, if you want to extrapolate that and go to three-dimensional space, then you have a cube. So each side of this cube is the same, right? And at each corner of the cube, we have lattice point. And you can see that in each lattice point now, we have placed a core or a basis. So this may be one single atom, or this may be so many atoms placed at each corner. And if we take this unit cell and repeat it translationally in a space, move it regularly, then we can create the whole solid. So a unit cell is very important because it tells us the smallest portion of the single crystal that you can study, which has all the structural characteristics of the single crystal. To create a large single crystal, you just have to translationally reproduce this unit cell. So this structure is very important. It's called the simple cubic structure, SC, where we have one atom. Let's think of the core as only one atom to make life easy. We have one atom at each corner. This atom is what we call the basis atom. Another cubic structure, exactly similar to the other one. The unit cell is the same, except now that the unit cell has an additional atom at the center. Okay, so you can think of this in 2 dimensions. You can think of this type of lattice where you have this type. Okay, so in 2 dimensions, you have something like this, and it's not completely regular, but as you can see that you have a line here of atoms, and then you have the next line a little bit displaced by half the distance, and then you have another line again which follows this line, and so on. So you can take this part here as your unit cell. So you have a point in the middle in your unit cell, a lattice point. And you can repeat it and produce all the lattice space. And this is exactly the extrapolation of this 2-dimensional structure to 3D, where you have an atom at the middle. This is again cubic. Each side here is the same length, but then we have an atom in the middle of the cube where the 2 diagonals meet. And this is the smallest unit cell that you can use repeatedly and translate it to produce the whole structure. So this is the smallest unit cell that you can study in this structure, and this structure is called body-centered cubic. Again, cubic because all these angles are 90 degrees and we have a cube with equal sides. All these sides are equal. So it's a cube, but the difference is we have body-centered, BCC. Okay? And then another one is the face-centered cubic, FCC. Again, the unit cell is a cube. We have an atom at each corner of this cube, but we also have an atom at the center of each face of the cube. So you can see that in this front face here, this front face, we have this atom at the center. And on this face here, we have this atom at the center. And on this back face here, we have this atom at the center. And at this bottom face, we have this atom at the center. We have no atom at the center of the cube, but we have an atom at each center of the 6 faces of the cube. So that's again another unit cell which has a cubic unit cell, but the lattice points or the bases are at all corners and at the faces of this cube. So you can see as we go from the simple cube, we have about altogether 8 atoms within the unit cell. Then we go to the body center where we have now 9. We have added another atom in the middle of the unit cell. And then now we go to a more packed or a more dense unit cell where you can see that here in this drawing in the unit cell, you have something like 14 atoms. Okay, so all of these structures are cubic, but they are slightly different in the number of lattice points, and therefore the number of atoms per unit cell. How do we define a plane or a direction in a crystal, a single crystal? Remember, here we're talking about a single crystal where we have regular periodicity of the structure, where we have a long range periodicity or order. So in a single crystal, and let's assume that what you see red here is one plane on this single crystal. How do we define this plane? How do we specify this plane? And the way to do that, here we have an origin, and this origin need not be one single origin in the whole crystal. You could again translate from one origin translationally to another origin. And as you can see, the way we define planes and directions does not depend or do not depend on where the origin is. If we translationally move from one origin to another, we still have the same representation for planes and directions. So let's assume that we choose this point as an origin, and then we have our A, B, and C basis vectors. And now we have this plane. So what we look at are the intersections of this plane with these three basis vectors. So as we can see that the intersection here is for M1 equals 6 points. And as you can also see that the intersection on the B-axis, M2, is equal to 3. And we can see that the intersection on the C-axis, which we call M3, is equal to, again, 6. Okay? So these are the intersections of this plane with the three axes. Then we take the reciprocal of this. Reciprocal is 1 over m. So 1 over 6, that is 1. And then the second reciprocal is 1 over 3. And then the third reciprocal is 1 over 6. Okay? Then we take the largest integers in the ratio of these. So these are 1 6, 1/3, and 1 6. If we multiply, if you try to make these integers, then we multiply by 6. So what do we get? We get 6 times 1 over 6, we get 1. 6 times 1/3, we get 2. 6 times 1/6, we get 1. And then we put this in a bracket like this, 1 to 1. So actually, 1 to 1 is how we define this plane. So this plane is called the 1 to 1 plane. So the plane, simply, you look at the intercepts of the plane with the three basis vectors. Then you take the reciprocals of these intercepts. And then you try to find the smallest integer in the ratio of these intercepts. And therefore, this smallest integer set defines the plane. So this is the 1 to 1 plane. Okay? So this is what is summarized here. And these 1 to 1, which I'm referring to here as HKL, these HKL are called Miller indices. Miller, of course, is the name of the scientist who first came with this representation. Why do we take the reciprocal? That will become clear when we look at an example, a solved example that we will be looking at as we proceed with this class. Okay, so we will talk about why we choose the reciprocals later. But this is the method. This is how we generate Miller indices. We also need to specify directions. We simply need to specify planes, and I showed you how to do that. But we also need to specify directions. As I told you at the beginning, again, this is very easy. And the way we do it is by writing the vector r along the specified direction, right? So we just take a point in the given direction and then write a vector from the origin to that point, and then take the smallest integers ratios in the same ratio and put them in a square bracket like 1, 2, 3. Like if I go back to one of the very first slides, this is slide here, and we have, this is my origin, this is a point, and I have written this vector r as 3a plus 3b. So these two integers, 3 and 3, define this